Okay. Hi. Um, Welcome to this week's Biome seminar. My name is Skylar Fetter. I'm a first-year PhD in YSE. This week, we are very excited to have Dr. Dan Fries with us here today. Over the past 12 years, the Yale School of the Environment has hosted this weekly seminar series called Biomes, Bridging Issues and Optimizing Methods in Environmental Studies, as our flagship forum for sharing cutting-edge research and impactful work. Dr. Fries is the Cochrane Family Professor of Earth and Environmental Sciences at Tulane University, specializing in blue carbon with mangrove, seagrass, and marsh ecosystems. His research focuses on carbon storage, carbon crediting, and coastal resilience to support climate change adaptation. He holds a Bachelor of Science from Imperial College London and a PhD in wetland geography from the University of Cambridge. Before Tulane, he spent over a decade at the National University of Singapore as an associate professor and deputy director of the Center for Nature-Based Climate Solutions. He's also part of the International Blue Carbon Initiative and the IUCN Mangrove Specialist Group, and serves as a co-editor-in-chief of Wire's Climate Change, supporting both impactful research and early career scientists. Please join me in welcoming Dr. Dan Fries.
Thank you. Thanks so much. Thank you for that kind introduction. Can you hear me okay? Yep. Awesome. Yeah, thank you. So yeah, I like mangroves. I like blue carbon, sometimes a little bit of seagrass. So I try to bring the seagrass into it by showing you still my favorite mangrove site in the world, but it does have seagrass as well, which you can see here. So we'll talk a little bit later about connectivity between these systems. This is Uvea Atoll in New Caledonia, a place that we've been doing a lot of work on carbon and how carbon changes with sea level rise since 2015. Okay, but before I start, all of the work that I'm going to show you has actually really been done by all of these folks. So I want to start out by thanking them for all their hard work. This is the Mangrove Lab, which is split between Tulane and National University of Singapore. But thanks for everything you're about to see is really their hard work. Okay, so why are we talking about blue carbon in the first place? Why do we even need this concept? It comes down to this graph and how we can avoid the worst of the ongoing climate crisis. And it doesn't really matter what way you look at how we're going to reduce climate change. We need to get our emissions down. We need to peak them, get them down, and that is obviously the hard work of decarbonization. But within that, there's going to be a certain amount we can do with land, with agriculture, forestry, and other land uses, either to avoid emissions going into the atmosphere, and once we get to net zero, then helping us to go beyond net zero to actively draw down carbon dioxide from the atmosphere. And really, this is where this kind of drawdown part is where natural climate solutions come into play, this kind of brown part in this IPCC pathway. And so natural climate solutions have become very colorful recently. We're starting to run out of colors, actually. I think but these are some of the main ones. And some of these colors are bad carbon. They are contributing to climate change, whether it's changes in ice albedo from glacial algae or carbon emissions into the atmosphere through black carbon. But at the bottom of the rainbow are the good carbon colors, green carbon, teal carbon, gold carbon, and somewhere inside there is blue carbon. So what is blue carbon? There's lots of different definitions, and we're actually spending a lot of time in the last year or two expanding the definition, but I'm going to kind of stick to a traditional definition for this talk. And it really refers to these four ecosystems: mangroves, marshes, seagrasses, and supratidal forests. And these are vegetated coastal ecosystems. And we call them blue carbon because they fit a number of these criteria. They're able to take carbon dioxide from the atmosphere at really high rates. They're able to store it at very high densities for timescales that are relevant to climate change. And so it's kind of two biophysical criteria. But then the rest of the criteria are really kind of management and policy criteria. that they're a blue carbon ecosystem because we can have a positive carbon impact by managing them in different ways or through restoring them. Importantly, that management should cause no environmental or social harm, which doesn't happen all the time, but it's something that we have to be very conscious of if we want to implement blue carbon effectively. And we can do all of those management steps in a way that we will have an appreciable impact on greenhouse gas emissions. So these 4 ecosystems fit most of these criteria. You might hear blue carbon talked about in the context of other ecosystems as well. Macroalgae, tidal flats, the sea floor, whales and fish, things like this. The science maybe isn't there for all of these ecosystems yet to know if we can tick all these boxes, but there's certainly, these are potential, or many of these are potential blue carbon ecosystems in the future, once we can address some important scientific knowledge gaps. And so these 4 ecosystems have attracted a ridiculous amount of interest in the last couple of years. When The Economist is talking about blue carbon, it's pretty mainstream, right? When Yale Environment 360 is talking about blue carbon, then I think we can, we're done, right? We're finished. We've achieved everything we need to achieve. So a lot of public interest and corporate interest in blue carbon, a lot of national interest. So we're seeing these blue carbon ecosystems incorporated into Paris Agreement targets of many countries. We'll talk about a little bit later. And that's leading to some really big plans for management and restoration. Indonesia restoring 600,000 hectares of previously destroyed mangrove forests. 100 million mangrove seedlings being planted in Mozambique. Some really big international targets, in part driven by interest in their climate mitigation potential. So within that context, I'm going to talk today about some of the science underpinning blue carbon. And I'm a geographer, so I like to look at this across different scales and how it changes across these scales from the local to global. But looking at these different levels is, which one is actually best for blue carbon management? Which scale is going to have the biggest contribution to climate change mitigation for blue carbon? Okay, so let's start with the local scale. And the local scale is really how a lot of people got interested in blue carbon in the first place. So this graph here is a systematic review we did of the sequestration rates of a range of different ecosystems. And you see that per unit area, per square meter, the rates of carbon sequestration in blue carbon habitats is significantly higher than many other ecosystems. Of course, these are averages and compilations, but we know that these blue carbon ecosystems have the potential to sequester carbon at really high rates. And that often results then in very high densities of carbon storage. So this is some field data we took from Singapore. These are relatively disturbed urbanized systems, but even there, the mangroves are able to store 500 tons of carbon per hectare, which when we compare that to terrestrial rainforests, has a very high density compared to some of these other ecosystems in Singapore. And this is due to where we find mangroves. We find them predominantly in the tropics, so these are very productive locations. And then for the storage, we have anoxic sediments, waterlogged soils because of tidal influence. And so we don't get the same kind of breakdown of the carbon that we do in other systems, and instead it accumulates over thousands of years, predominantly in the soil column. So, in a seagrass, 95% of the carbon is in the soil. In mangroves, it could be 60 or 70% of that carbon is locked away in these soils. But of course, a focus just on sequestration and stocks, which is where a lot of blue carbon knowledge started, actually hides a lot of other stuff going on, right? And this spaghetti diagram is meant to scare you into how complex blue carbon is. And of course, we can't measure every one of these bubbles and links, but we can at least estimate numbers. And this is an assessment we did for a mangrove restoration project in North Sulawesi in Indonesia a few years ago, trying to understand the relative contribution of all these different pools. So there's a lot going on that we need to understand in the blue carbon cycle at a very local scale. The carbon going in, the carbon leaving through emissions, and then all the transformations in between, including between ecosystems, so between mangroves and seagrasses, for example, through lateral exchange. So the local scale is already a lot to understand. And even within the local scale, there's intra-site variation of all of those different processes as well. So they're not the same depending on where you are throughout the site. And I'll show you just one study to give you an idea of this. All of these graphs go from kind of the landward side of the mangrove out towards the sea, to the edge of the mangrove, then into the tidal flat. And depending on where you are, even along that transect, and we're talking in the scale of meters here, right? Within a few meters, we get changes in carbon stocks on the top of the soil, and in the fluxes of CO2 being emitted from the soil. And so we get a peak in kind of the pioneer seaward zone of the mangrove of CO2 emissions, related to different species and their different root structures, as well as different microbial communities in the seaward area of the mangrove, which is flooded more regularly by the tide. So within a few meters, we have all of this complexity, and all the numbers in that graph are changing. Okay, so, and then if the landscape, if the local scale wasn't confusing enough, if once we go up to higher scales, we see again more spatial variation. This is a remote sensing study of mangrove above ground biomass as a proxy for above ground carbon. And this is again just in the landscape of Singapore, very human modified landscape. And you can see variations in areas of high carbon density in orange, areas of low carbon density in yellow, and different patterns. And if we zoom into some of these are the patterns of human disturbance. These are old aquaculture ponds where mangrove was cut down, mangrove has then grown back, but has not yet reached the density of surrounding mangroves. So we definitely see spatial variation in terms of human impacts on this landscape scale. But on the landscape scale, we get a lot of other physical parameters which are also changing on this scale, and particularly the coastal geomorphic setting. So we can compare, kind of classify our coastline into different types of coast. Sediment-dominated systems, particularly deltas, so dominated by fluvial sediment input, so river-dominated systems. Systems on high-energy coastlines, so wave-dominated, particularly lagoons, and then we'll often get blue carbon ecosystems in the kind of the quiet part behind the lagoon on these high-energy coastlines, and tide-dominated systems. And we have known for a long time that depending on what type of coastal landform you're on, that's going to affect the amount of hydrodynamic energy you experience, the amount of sediment deposition you experience, and all of these things we know are going to influence carbon. And we've seen that even in our own studies, again, some examples from Singapore, and looking first at where the carbon is coming from. So we have different sources, the carbon into a system. It can be produced within the ecosystem, autochthonous carbon production, or we can get it from outside the system. And we can get it from oceanic sources or from nearby ecosystems such as algal beds and seagrass meadows. And we can get it from the terrestrial zone as well. And the balance of those different sources changes depending on what geomorphic landform you're on. So if you're on an open coast setting, you get more oceanic inputs of carbon. If you are in an estuary, you get a lot more terrestrial input of carbon. And this is the brown part on this graph for Sungai Buloh, which is an estuarine mangrove system. So it's going to change the type of carbon that we're working with. And then that translates into changes in soil carbon stocks. This is actually an example from a seagrass study. And we see that we have, again, different levels of soil organic carbon in tons per hectare, depending on if you're in an estuary, lagoon, or associated with a coral reef. Now, we've taken those different geomorphic settings and actually applied them to the global scale to understand, do these landscape patterns still hold globally? And so this was a modeling exercise we did a few years ago now, using various spatial data sets to classify the world's mangrove forests into these different, 4 different coastal geomorphic settings: lagoons, deltas, open coasts, and estuaries. And we found that 40% of the world's mangroves are deltaic, so these big sediment-rich minerogenic landforms. And so only 10% are what we would call biogenic mangroves, where there's not a lot of sediment supply, and instead the carbon is coming from autochthonous sources, so root production, leaf litter, and other biological sources. And really mineral sediment input and carbon from outside the system is probably not as important. These systems are disconnected from river systems, for example. And particularly in Southeast Asia, where I do a lot of my work, is where we get a lot of deltas, open coasts, and estuaries, and not so many of these biogenic settings, which are more found in the Pacific, the Caribbean, and some parts of the Gulf of Mexico. This has big implications for how we think about carbon, because a lot of our early mangrove studies happened in the Gulf of Mexico and the Caribbean, because it was close to US universities, right? If we think 100 years ago. And so a lot of our understanding of mangroves were based on these biogenic systems where root production is really important. And it turns out that they are not fully reflective of the world's mangrove forests. So then when we try to apply those kind of principles to Southeast Asia, it didn't really work. But now we're getting a much more holistic and global understanding of different mangrove systems across these different settings. And we see this impact of these settings on carbon. So this is now not a landscape model of above ground biomass, but a global model of mangrove above ground biomass. And you can again see a huge spatial variation with high densities of above ground biomass along the equator, particularly Indonesia, West Africa, and the west coast of South America, where we are equatorial, we have high temperatures, huge rainfall, and we're not really affected by disturbances such as cyclones. So we get trees that are 40 meters in height and higher, while if you're in Baja California in Mexico, the tree is a meter high, right? It's still the same, often the same species or same genus, but we have huge plasticity in the growth forms. And of course, a tree this tall is not going to store as much carbon as a tree that's 40 meters tall. And so this model came from a huge field effort. Over 100,000 trees were measured that went into this model. I did not measure all 100,000 of the trees, measured a few thousand maybe, but this is a huge international collaborative effort of a range of published and unpublished tree carbon stock data points, combined then with a number of climatic and these geomorphic landform variables. And certainly there's a climate influence in this pattern. There's a disturbance influence of cyclones in this pattern, but we also see a geomorphic influence on this pattern. And so these are those different coastal geomorphic settings, and we see above ground biomass ranges are different, again, these are global averages, so they're a little wide, and they incorporate, changes in climate and things. But we see generally differences in the above ground biomass according to environmental setting. This is for above ground biomass. Interestingly, we see the same kind of influence of geomorphology on the soil carbon as well, but often it's the inverse. So actually across these different settings, the actual amount of carbon in the soil and the vegetation might be, if we take climate into consideration, might be about the same, but the ratio of the vegetated carbon versus the soil carbon might be different across these different coastal settings. So we know that geomorphology is one very important landscape and global driver. So that was looking at stocks, and now let's look at the global variation in the amount of carbon coming in. So this is a model that tries to approximate the distribution of gross primary productivity as one input into the system. It's using MODIS satellite imagery linked to eddy covariance towers. And it basically shows the long-term 20-year changes in productivity. So are these systems greening or are they browning? And we can see over 20 years, almost 40% of the mangroves around the world showed an increase in productivity over that time period. 10% showed a decrease in productivity. And in particular in North Australia, where we had a huge dieback event, where within a few months, 1,000-kilometer length of mangrove died due to ENSO changes. And what was interesting in this study, we also compared this to neighboring evergreen broadleaf forests. And generally, the mangrove showed a greater increase in productivity over that period compared to tropical broadleaf forests. But mangroves were also much more dynamic, so much more sensitive to a range of climatic changes. And a follow-up study we're doing now is showing that that is really driven by ENSO and the Indian Ocean dipole and changes in sea level and changes in precipitation primarily. So mangroves are, showed greater increase in productivity, but it's a riskier increase in productivity and is much more sensitive to landscape scale climatic changes like we saw in Australia. Okay, but those fluxes will translate ultimately into a spatial distribution of stocks, including soil. And this is now for all blue carbon ecosystems, not just mangrove forests. And you can see that there are some real blue carbon powerhouses around the world. Brazil, Australia, Indonesia, and surprisingly the US as well, because of our extensive tidal marsh area that we have within the US. So we think generally, as much as 10,000 teragrams of carbon are stored in mangroves alone. When we include all ecosystems, it's well over 30,000 teragrams of carbon. There's a lot of uncertainty in this, in part because of the uncertainty in the global area of seagrass. We have good maps of global mangrove extent. We now have good maps of global tidal marsh extent. We still do not have a global seagrass map, which is really constraining how we can incorporate seagrasses into some of these kind of global patterns and understanding. But unfortunately, we have all these stocks, but they're being lost at very high rates. Maybe not as high, or at least for some ecosystems, not as high as we were losing them historically, where in the late 1990s, we assumed that mangrove forests were one of the world's most threatened ecosystems on the planet, being lost at 3% per year. We now, through remote sensing, think that that's probably more like 0.2% per year. So an order of magnitude reduction, but still a lot of loss. Now, this gives us an opportunity for blue carbon management. If you think back to those criteria for blue carbon, one criteria is that we have to be able to manage them in a way that has a carbon benefit. And if we're losing these ecosystems, then that gives us an opportunity to turn that around. And instead of releasing that carbon that's stored in those ecosystems, we keep it in the ground through avoided emissions, through avoided habitat loss. So if we do conservation, that's a good way of increasing the carbon balance. And of course, we've lost a lot of ecosystem. So that gives us opportunities to restore those areas that used to be mangroves or seagrasses, and we can bring them back. So we have options through restoration, and there are other management techniques we can do as well that would have a positive impact on the carbon balance, for example, by flooding an area that reduces methane emissions, as one example. And this study tried to get at what the global contribution of those different management actions might be on a global scale for all three of these blue carbon ecosystems. And the map here shows that Indonesia probably has the highest potential for climate change mitigation, in part because of high rates of habitat loss and high potential or large areas that are potential for restoration. And so this paper calculates, what that looks like in terms of the amount of carbon. Mangroves probably have the biggest avoidable, avoided emissions potential. And then panel F is the restoration potential. And we think probably seagrass has the biggest potential for restoration. And when we combine all of those, we can get an understanding of what that means in terms of carbon. So conservation and restoration of mangroves, probably about 800 teragrams of carbon dioxide per year. Now, a bit of a caveat to what these scenarios are, because that sounds too good to be true maybe, right? These graphs assume zero habitat loss, so that we are getting deforestation down to zero. That would be nice. And in some countries, that is actually already the case. But globally, that's going to be very hard to do, right? So this is the most optimistic conservation scenario we could think of. In terms of the restoration numbers, these are the areas we think are biophysically suitable for restoration. For mangroves, it comes to about 800,000 hectares globally, based on a number of biophysical parameters, previous land use, and other things. We'll talk about in some subsequent slides that biophysical potential of restoration is different from actual feasible restoration. So again, these are two absurdly optimistic scenarios, right? But if in an ideal world we could do those two things, we would avoid 300 teragrams carbon dioxide per year. We would restore 800 teragrams of carbon dioxide per year. And that would, altogether, that's 3% of global fossil fuel emissions, which doesn't sound a lot, right? So this is kind of the reality check, I think, right? Blue carbon, and you hear a lot about it, it is not the get out of jail free card. It is not the silver bullet to solving climate change. It does not get us away from doing that really hard job of decarbonization that you saw in that IPCC pathway, right? You really have to do that first. But this, will help in some situations, but again, globally, we can't expect too much of these ecosystems, right? And it's understandable. They are, these are found along our coast, right? So I showed you this graph earlier, one of the beginning slides about the sequestration rates per unit area. I was a little bit cheeky. I did not show you the full graph. The rest of this graph actually then looks at habitat area. And these coastal ecosystems are constrained to a very thin coastal margin. So their area globally compared to other ecosystems is tiny. So their actual sequestration for the whole ecosystem, is like 1% of vegetated carbon sequestration, right? So this is why on the global scale, blue carbon is going to be challenging. We just do not have a lot of blue carbon compared to these other really important natural carbon sinks. So if the global scale is not going to work for blue carbon, what scale is, right? So let's look at the national scale, because actually, if they're not important globally, that's not necessarily a bad thing, because we don't manage climate change globally. I know that sounds a bit weird, but we don't, we manage it nationally, right? We manage it through the Paris Agreement, through nationally determined contributions. So every country makes its own contribution. And of course, all those contributions add up to the globe, right? But we don't manage it on that global scale. So does it work on the national scale? Let's see. When we've compared the sequestration of mangroves versus individual countries' fossil fuel emissions, so not doing it at the global scale, but looking at it per country, then it's a slightly different picture. That there are 17 countries where existing mangroves sequester enough carbon to offset more than 5% of fossil fuel emissions. Now that becomes a little bit more important, right? So not every country is going to be able to do this, but if there's one solution that one country can do to offset 10% of its emissions or 12% of its emissions, that's worth doing, right? That's now a more sizable impact. And there are another 17 countries where it's between 1% and 5%, right, of fossil fuel emissions. And this is the distribution of those countries. And they are often countries with large mangrove extents and relatively low fossil fuel emissions, right? So that balance works out a little bit more. This is only for mangroves. Unfortunately, we don't have the data for marshes and seagrasses to do this yet. But I would imagine with seagrasses in particular, there would be more countries added to this list. So for some national contexts, actually, it could be a pretty decent contributor. And there's another set of countries that also have something to add to this, which is small island developing states. They're often, because their islands have extensive blue carbon resources and not much green carbon or other ecosystems. And particularly, and again, if we did seagrasses, this would be even higher again. So there are a number of small island states where if we could get mangrove loss to zero, it would offset more than 10% of their land use emissions this time. I'm not comparing to fossil fuel emissions. I thought that was a little bit unfair, right? We can't expect mangroves to offset fossil fuel emissions, but maybe land use emissions is a more feasible scenario. So these are countries where actually blue carbon could make a difference. And that's exactly what we're seeing. If you go through the national greenhouse gas inventories and the nationally determined contributions to the Paris Agreement, you see a range of blue carbon targets. Some of them are in terms of area planted. Some are in terms of the amount of carbon they wish to sequester through blue carbon by 2025 or 2030. And these nationally determined contributions are updated regularly, and there's a ratchet mechanism. So each NDC every 5 years has to be more ambitious than the last one. So we're seeing more and more blue carbon targets as these NDCs get updated. And there are a number of countries that are in the process of including, or at least thinking about including blue carbon in their upcoming national greenhouse gas inventory and NDCs. And there are a number of countries, and I'll just pick, again, Singapore, since we've seen a few examples. And we have a project where we are working with the Singapore government to do exactly that, to see how we can put blue carbon into the national greenhouse gas inventory, and then what targets for the NDC would that look like for mangroves, for seagrasses, and we're also going to try it with tidal flats, which are potentially a candidate blue carbon ecosystem, but are under threat from development. So, this is good news, right? And countries already see that in their national context, blue carbon could make a real difference. And then where there's been, so that's kind of at the national scale. Now let's look at the local scale. And local scale is where we get a lot more interest in things like carbon credits. So protecting or restoring a blue carbon ecosystem and to generate carbon credits that can be then purchased on markets and used for offsetting and things like this. And in this model, we tried to get an idea of what is the scope for carbon credit projects. Again, just in mangroves because of spatial data availability. But which are the landscapes which we think are going to have the most potential for this? And there's a lot of different spatial data sets that go into this. Obviously, the distribution of carbon, all those maps I showed you earlier. So where the carbon is threatened, so that we could avoid, by taking that threat away, we could have avoided emissions. So this aspect of additionality, which is very important in carbon credit projects, plus some very kind of coarse metrics of economic aspects, so project costs, project maintenance costs, these kind of things, how much a carbon credit sells for on the open market, and a bunch of other things. We threw them all into this model, and it comes up with 3 different types of mangroves. One where the cost of doing a carbon credit project is going to outweigh the money made by selling carbon credits. So those are considered non-investable. I should say, I hate these phrases, by the way, right? Mangroves should not be profitable or investable. But this is the language we used in this paper. That doesn't mean these non-investable mangroves are not important for many other things as well, right? But there are some mangroves where there is a threat to those mangroves, and they are in, maybe the cost of the project versus how much would be generated by selling carbon credits just about breaks even. These are the ones in kind of purple. And then the ones in green is where they might be able to produce so many carbon credits at particular prices that they actually would outweigh the project cost, and that would generate additional conservation finance. And actually, it turns out that in this very kind of hand-wavy model, which I could pick apart just as much as anyone in the audience, but with these coarse metrics, 20% of the world's mangroves would qualify for carbon financing, which is a huge number, which is great, right? No, it's terrible. It means 20% of the world's mangroves are at risk, and we could protect them through avoided emissions. So it's actually startling that that number is so high still. But if we could do projects across all of these, it might generate in excess of $1 billion a year in conservation finance. So big numbers, right? And big potential. So despite that big potential, I can count on one hand how many carbon projects we have in blue carbon ecosystems. And this is the map here. And with a few examples, these are the ones that have been verified on an international carbon registry. Not all of them are selling credits at the moment. Only a handful are, right? So how, we have this huge potential and we're not seeing it on the ground, right? We're getting nowhere near to that $1 billion a year, right? The pipeline is getting better. There are more projects coming online and there are inquiries every day and people wanting to set up projects and do pre-feasibility assessments and all this stuff. And we're seeing some seagrass projects coming online too. Including one in Chesapeake Bay in the US, which will be the world's first seagrass blue carbon credit project, and is very close to being verified. But the pipeline is getting better, but it's still not matching that potential. So why isn't it matching that potential? Well, there's a number of reasons. One, our model was completely useless, and so we completely overestimated, which might well be true. But a number of these kind of spatial prioritization exercises that show potential show this mismatch with what's actually happening on the ground. So it's not just our model. And it turns out there's a lot of barriers to doing these projects on the ground, which might not be surprising to you, right? And some of them are scientific, for sure. We have a good handle on stocks. Some fluxes are hard to measure, and doing it in a cost-effective way is challenging. But actually, the scientific constraints are not huge, in my opinion. I know we're not supposed to say that as scientists, right? Because we still want funding. And there's still interesting questions, but we can do carbon credit projects today with the science that we have. So really, it's these constraints, right? There's land availability. It's the cost of these projects. It's conflicts between national scale carbon accounting and commercial carbon accounting. It's land tenure issues, community benefit sharing issues, all sorts of things. And I'll give you just one example. This is for mangrove restoration and all the constraints that we see in a mangrove restoration project, right? And the majority of them are these kind of socioeconomic governance constraints, right? There are some kind of biophysical constraints, and some of these would be linked to science. But these are really the reasons why governance and socioeconomic parameters push restoration projects into unfeasible locations. But we know they're unfeasible, so that's not a science gap. But these broader legal governance and community and socioeconomic issues push these projects into these places. And really, they are the boundary conditions in which the science constraints operate, right? So it's these kind of questions which we need to really overcome if we want to meet anywhere near the potential that our scientific studies show is out there, right? So in summary, scale is really important in blue carbon, whether it's local, landscape, or global. And scale certainly means that blue carbon is a very efficient natural climate solution. I don't want to use the term effective, because effective will depend on the scale that you're on. But these local scale points that got people interested in blue carbon in the first place certainly make it a very efficient natural climate solution. We know that the bigger in scale you get, the more we have to consider the physical environment, climate, and particularly geomorphology in understanding blue carbon dynamics. And we know that those data give us an idea that there's that there is global scale opportunities, but really the huge opportunities are really at the local or the national scale. That's where we're going to realize these global opportunities. It's not really going to be achieved at the global scale itself. But achieving them and realizing whether it's national accounting or local scale carbon credit projects is somewhat determined by science, but it's really determined by these different multidisciplinary barriers and constraints. Now, the good news is there's a lot of people working on those constraints, and you have some of them in the room with Blue Forests from Indonesia here, who are tackling exactly some of these community and land tenure challenges. But these are small on-the-ground interventions, right? Land tenure is such a diverse, even across a single landscape, let alone globally, that it's not a thing we can tackle at that scale. You have to go on the ground and negotiate these things for individual sites, right? So that is small-scale work. It's slow. You don't go in there, negotiate a land tenure arrangement in a day and leave, right? These are months or longer of negotiation. It's hard work. It's slow work. But this is the work we need to do if we actually want to get anywhere to using blue carbon as a natural climate solution. Thanks very much.
All right, we have time for one or two questions. And
Hi, my name is Maya, and I had a question about how productive blue carbon ecosystems are when water is contaminated. Excuse me. I know in India, a lot of coastal communities facing a lot of contamination due to textile dyeing, and it's really harming, creating a lot of water in those ecosystems. So I'm just curious to know if other chemicals, toxic chemicals, prevalence in the ecosystem impacts the carbon sequestration.
Yeah, this is a really hot topic at the moment because a number of our mangroves, as well as seagrass, is actually maybe even more sensitive to some of these kind of water quality issues. But if I just talk about mangroves, which I'm most familiar with, it depends a little bit on the pollutant or the stressor. But generally, degraded systems are less productive, and we see that in many examples. But it depends really on that stress. So if it's an organic pollution issue, for example, that might just change the allocation of where carbon goes. So we might get less root production, more above ground production or something due to changes in nutrient availability. If it's things like oil, again, very severe oil spills can be hugely detrimental to mangrove productivity. And we see this particularly in West Africa, where there are huge issues with leaking oil pipelines and oil spills and things like that. And there we have heavily degraded systems. In those systems, I'm not so worried about the carbon. I'm more worried about all the other benefits that those systems are providing to the coastal communities living there, right? We also see huge impacts on fisheries, as an example, right? And shellfish collection and things. So yeah, I mentioned that just to, we shouldn't remain fixated on carbon, right? And these are living landscapes that people throughout the tropics really rely on. But yeah, pollution can be a real important source of degradation. And we focus here a lot on deforestation and changes in habitat area, but changes in habitat quality is also really important driver and process in the carbon cycle. Thank you for the question.
one more quick question.
Hello, great talk. My question is about sea level rise in mangrove forests, and if there are some species of mangrove that do better with like saltier water versus more brackish water, and how that plays into the reforestation plans.
Yeah, sea level rise is a huge issue. Not in all mangroves around the world. It's not a complete 100% doom and gloom scenario, but in many locations around the world, we're very concerned of that. And there definitely are species-specific responses, and we expect, as sea level rise continues, that we see shifts in species. So there are some species, particularly at the seaward edge, that are more tolerant of inundation, more tolerant of salinity, and we would see them replacing more biodiverse landward mangrove communities. Though, of course, there's going to reach a point where even those more adapted pioneer species are beyond their tolerance threshold, and even they are lost, and then we get a conversion to a seagrass or an unvegetated mudflat. And then the second part of your question was, how do we think about that in terms of sea level rise? In terms of restoration, sorry, right? In some countries, that is taken into consideration, but and again, we have some restoration experts here, but generally planning for sea level rise is a luxury that many restoration projects don't have, right? Many restoration projects, though not all, are very opportunistic, where a piece of land becomes available or is negotiated, and you can do it there, right? And and there are things we could do, like plant or encourage mangroves to colonize at the highest elevations to give them the most time for sea level rise. Or in Australia, they're starting to think about how they can secure land, which is currently terrestrial land, but under sea level rise scenarios might become flooded and potential habitat for mangroves. So in some places we can do that kind of stuff, but generally, we're not thinking on those timescales for restoration generally, right? Because we just want to get mangroves in the ground. But where there are opportunities to, then sure. And I think speak to the Blue Forest crew they're down here, how they do that. Yeah. Thank you for the question.
All right, wonderful. Can we just give one last thank you to Dr. Freese?